pleasant day, everyone. I am Bernadette de la Cruz, together with my groupmates, are going to discuss the first law of thermodynamics. Thermodynamics is the science of energy, and it covers all forms of energy, including thermal, chemical, mechanical energy, and many more. So thermodynamics is a combination of four laws, and now we're going to discuss the first law of thermodynamics. Every day is a continuous process of using energy, but it doesn't mean that energy is losing. And that's what we're going to tackle about this law. The first law of thermodynamics is basically stating the law of conservation of energy. It affirms that heat is a form of energy. Therefore, it means that heat also cannot be created nor destroyed. However, it can be transferred from one location to another and converted to other forms of energy. It deals with the total amount of energy in the universe, and in particular, it states that this total amount does not change. In the first law of thermodynamics, it is stated that the amount of energy in the universe is constant. But how? In a system, there's a presence of internal energy given, which includes the potential and kinetic energy. With the interactions of heat, work, and internal energy, there are energy transfers and conversions every time a change is made upon a system. And during that interaction between a system and its surroundings, the amount of energy gained by the system must be exactly equal to the amount of energy lost by the surroundings. Means that no net energy is created or lost during these transfers. That's why the amount of energy in the system remains the same all the time.
Since first law of thermodynamics is the principle of conservation of energy because of its statement of transferable energy, it serves as the foundation for heat engines, chemical reactions, power plants, and many more. The most common example of it is the light from the sun, radiant energy, which transferred into chemical energy by plants. The energy that enters to the system in a form of heat is equal to the sum of the increase in system's internal energy, while the energy that leaves from the system in the form of work done is by the system on surroundings. The formula for first law of thermodynamics is delta U equals to Q minus W. Delta U is the change in internal energy of the system. Q is heat added from system in surrounding. W is the work done by the system with its surrounding. The international system of unit is J, or Joule. All in all, first law of thermodynamics is important as they control interactions of everything in universe.
The limitation of the first law of thermodynamics. First law of thermodynamics does not say anything about whether the process is possible or not. You see in the figure 1 that in the engines, the chemical energy of the fuel is converted into useful mechanical work. But we cannot convert this mechanical energy back into fuel, or in other words, engine cannot produce fuel back. We all know that this is practically impossible. Fuel cannot be obtained back, but the first law of thermodynamics does not say anything. First law of thermodynamics does not say anything whether a process is spontaneous or not. For any chemical reaction, the direction of the reaction, forward or backward, depends on the Gibbs free energy, and it is closely related to the definition of entropy. And the essence of the entropy comes from the second law of thermodynamics. First law of thermodynamics does not address this issue. The limitation of first law of thermodynamics is it does not say anything about the direction of the flow of heat. Suppose heat always flow from high temperature to low temperature region. If we want the opposite, we have to do some work. First law of thermodynamics does not confirm that.
The first law for closed system. The first law simplifies states that energy cannot be destroyed or created, merely converted from one form to another. According to thermodynamics, a closed system can exchange energy in the form of heat and work. A closed system can exchange energy with its surroundings through heat and work transfer. In other words, work and heat are the forms that energy can be transferred across the system boundary. In a coal-fired power station, heat is converted into work and electricity. The first law gives the relation between the three forms of energy encountered: heat, work, and internal energy. Usually, the substance contained in the piston cylinder arrangement is taken as the system. Heat is added to the system, it expands and raises the piston performing work. In undergoing process, the first law states that energy is conserved. This means that the amount of energy is in the beginning, the total internal energy plus the amount of energy transferred to the system, the heat Q in, must equal to the work done by the system, plus the amount of energy in the system at the end of the process, the total internal energy. What is heat transfer? Heat is defined as the form of energy that is transferred between two systems by virtue of a temperature difference. Take note that there cannot be any heat transfer between two systems that are the same temperature. This is my example. Electrical work. A well-insulated electrical oven is being heated through its heating element. Determine whether it is work or heat. Interaction. Consider two systems. A. The entire oven including the heater, and B. Only the air in the oven without the heater. The energy content of the oven is increased during this process. So the solution in letter A is the energy transfer to the oven is not caused by a temperature difference between the oven and air. Instead, it is caused by electrical energy crossing the system boundary, and this is a work transfer process. The system boundary includes the outer surface of the heater and will not cut through it. Therefore, no electrons will be crossing the system boundary. Instead, the energy transfer is result of a temperature difference between the electrical heater and air. This is a heat transfer process.
Now let's move on to the application of the first law of the thermodynamics. So, heat is a kind of energy according to the first law of thermodynamics. Hence, thermodynamic processes are governed by the concept of energy conservation. So, as a result, neither heat or cold energy can be created and not be destroyed. It may, however, be moved from one region to another and changed into and out of other types of energy. So, there are three applications of the first law of thermodynamics. These are isothermal process, melting process, and the heat engines. So first, let's talk about isothermal process. So the temperature of an ideal gas remains constant during an isothermal process. So this means that the heat supplied to the system is being utilized to do work against the environment. So another process is what we call melting process. So when a solid melts to liquid, its internal energy increases. Let M is equal to the mass of liquid and L is equal to the latent heat of the solid. Amount of heat absorbed by the system is dQ is equal to mL. The most common practical application of this law is the heat engine, which is the last part. Heat engines convert thermal energy into mechanical energy and vice versa. Most heat engines fall into the category of open systems. So the basic principle of a heat engine exploits the relationships among heat, volume, and pressure of working a fluid or any substance that flows. So it is typically a gas. When a gas is heated, it expands. However, when that gas is prevented from expanding, it increases its pressure. So if the bottom wall of the confinement chamber is at the top of a movable piston, this pressure exerts a force on the surface of the piston, causing it to move downward. So this movement can be harnessed to do work equal to the total force applied to the top of the pistons times the distance that the pistons are able to move. So now, refrigerators and heat pumps are heat engines that convert mechanical energy into the heat. So most of these fall into the category of the closed system. When the working fluid or gas is compressed, its temperature is increases. So this gas can then transfer heat to its surrounding and environment. Then, when the compressed gas is allowed to expand, its temperature becomes colder than it was before and compressed because some of its energy was removed during the hot cycle. So, this cold gas can be absorbed heat energy from its environment. So, this is the working principle behind an air conditioner. So, air conditioner don't actually produce cold, they remove heat.
So we have sample problems about the first law of thermodynamics. The first one is 3000 joules of heat is added to a system and 2500 joules of work is done by the system. What is the change in internal energy of the system? In this problem, we will find the change of internal energy of the system and the given values are positive 3000 joules for heat or Q and positive 2500 joules for work or W. Please remember that Q or heat is positive if the heat added to the system and W or work is positive if work is done by the system. Q is negative if heat leaves the system and W is negative if work is done on the system. Again, the equation of the first law of thermodynamics is delta U is equals to Q minus W. We only need to substitute the values. 3000 joules minus 2500 joules is equals to 500 joules. So this is the final answer, which means that in this problem, internal energy increases by 500 joules. The next one is 2000 joules of heat is added to a system and 2500 joules of work is done on the system. What is the change in internal energy of the system? In this problem, we are looking for the internal energy of the system and the given values are positive 2000 joule for heat or Q since heat is added to a system and negative 2500 joules for work or W because work is done on a system. Again, the equation of the first law of thermodynamics is delta U is equals to Q minus W. We only need to substitute the values. Delta U is equals to 2000 joules minus negative 2500 joules in subtracting integers. We have a rules that we need to get the opposite sign of the second number or subtrahend. Then proceed with the regular addition of integers. 2000 joules plus 2500 joules is equals to 4500 joules. In this problem, the internal energy of a system increased by 4500 joules.